Okay, so welcome to review session 5. Um, Today we're going to be talking about transistors briefly. Specifically, you're going to be doing a BJT, uh, op amps, and that's kind of it. So we're going to have the like model of non-ideal, or like the I'll say non-ideal and non-ideal. I think that's all I'm going to go over. You just make sure. And then along with that, like there will be some review of some other stuff. Like I'll briefly touch max power as well. Uh, I know there was some trouble with the homework this week from a lot of people, so I'll go over a couple of the homework questions. And then I'll do kind of just a lot of op-amp questions. So yeah, to start, I'll go over briefly the transistor model you learned in class. So for the BJT little lesson, right? BJT is the bipolar junction transistor. I spelled it wrong already. No, I didn't. Polar junction transistor. If we're being really technical about it, this is an NPN transistor, which means something that you will learn in ECSE 321 if you care to learn it and you are an electrical engineering major. But basically, the idea with this is that we can model this as we have we call this the base, the collector, and the emitter. So we'll have our base here, and our base, we can kind of just think of it as having, yeah, yeah, we can just kind of think of the base for the purposes of our model here. We can just think of it as roughly, it's usually like about 0.7 volts. You have a voltage source there. You have your emitter on the bottom, and then your collector. This is the most important part, is a dependent current source with a value of beta times the current going through the base. So if this is the IB, right, then we can say IC equals beta IB. And then by Kirchhoff's current law, these two currents would add together, and we know that IE is 1 plus beta, because we have beta times IB and we have IB here. So if you add those together, you'll get 1 plus beta times IB. And for the purposes of this class, this is kind of all you really have to understand. Um, Basically, the idea is whenever you have a circuit where you have a BJT, take your three terminals, your base emitter and collector. Here we have the base emitter and the collector, and just replace this with this. And then once you've done that, you know how to deal with circuits that involve voltage sources and dependent current sources now. So once you've replaced the circuit, it's basically identical. And that was the case as well with problem 2 on the homework, which I will briefly go over. And then I think I'll stop talking about transistors for the day unless people have more specific questions.
Are we mostly gonna be given the value for beta?
Yeah, you should always be given the value for beta. Usually beta is like about 100. Um, if you're using like transistors in the real world, it'll say what the beta is on the data sheet. Um, and yeah, but it should be given to you. There's like other equations you'll learn about transistors. If you're an electrical engineering major, you'll learn a lot more about them in your future classes because it's kind of the foundation of a lot of modern electronics. But for the purposes of this class, just kind of know this model. It's just a voltage source and this current source. And you know that you have some current flowing through the beta side or through the base side, and then the voltage through the collector side is beta times that current. So basically, you can think, okay, if I have some current flowing here, I will have maybe 100 times that current flowing here. And that's the reason it's useful. Because if you can like in real life, when you want to use this, you have some kind of small current going in here, and you use that to control a big current here. Yeah. Okay, so the question on the homework was something like this. Um, yes. Okay. And it was saying, okay, what is V out over V in, basically? So to do this, the first thing we're going to do is we're going to drop in our equivalent circuit model that I just showed. So this, if we drop in that model, I'm going to kind of rearrange some of the wires, but all of the connections will stay the same. So we'll have, still have that up there. And then here we have that dependent current source with a value of beta times IB. And then that goes to the emitter. So we can think of this as the collector, emitter, and then here, down here, we'll still have that V in. And our RS. And then here we'll have that kind of 0.7 volt-ish source. For the purposes of this question, they do say that assume. Oh, my roommate just started vacuuming. Let me close the door. Oh, never mind. If you can hear that, it sounds like someone is like drilling into my roof right now, so that's lovely. But I will just keep talking. Um, anyway, I'll
It
just call
seems like
this.
you have noise canceling, so we are not hearing anything.
Oh, okay, that's good. I guess Zoom is good at that. I'll just call this VBE for this voltage source. And it does say for this question, assume VBE is very small, so we can basically just ignore this. However, again, we have to label, okay, through here we have IB, and then this is beta times IB. So again, what we want to find is the voltage here, and the voltage here, very simply, this was called RL, is going to be V equals IR, right? So it's going to be I times RL. I here, since this is on this branch, right, it's going to be beta times IB times RL. So what we have to do is we have to find beta, right? So, and we can do that by just kind of writing some loop equations. If we want to do a loop equation, well, there's two loops here, right? We have this one and we have this one, right? So I'll start by doing an equation on that inner loop. So on the
Is
inner
it
loop,
also possible to take like the bigger loop outside instead of inside?
yeah, you can do that as well. Any of them will work. It's just you have to that one might not get basically you'll have to get two equations where you have two unknowns and then you can solve. And if the outer loop also works, then that also works fine. There's definitely many ways to do this. However, in the the answer key on the homework, this was the one that was done, so that's the one I'm going to go with right now. But yeah, as long as you get two equations where you have two unknowns, then you can solve for it. Um, but anyway, on that inner loop, so I'll label this blue. On the inner loop, we're going to have minus Vn, right? Plus, oopsies, plus Rs times IB, right? Because we've defined that as IB. And then on that emitter resistor, the RE, well, we know we have IB flowing in here and beta times IB flowing in here. So as before, that means down here we'll have beta plus 1 times IB. So we have, so inner loop, I'll label that. So here, then we have RE times beta plus 1 times R times IB. and that equals 0. So again, we're trying to solve for IB, and in this case, actually, we can just kind of do this from this one equation, right? So what's this going to get us? We know, oh, and I did kind of ignore VBE here, so technically it should be plus VBE plus that, but we're going to cross that out because the question said to ignore it. Um, anyway, when you shuffle things around, we're going to get IB, let's see, RS IB plus beta plus 1 RE IB equals VN, right? And then from there, we factor out IB and divide, right? We'll get, um, yeah, if we factor out IB and divide, we'll get IB equals Vn divided by Rs plus beta plus 1 times Re, right? Pretty straightforward. Just with that one equation, we did that. Then we actually don't even need to take an equation for that outer loop because, as I said earlier, we know that the voltage across this resistor V equals IR. We know because there's a current source here that the current is going to be beta times IB, and RL is just like a number that would be given to us. So we can already here just say, okay, V out is going to be beta IB times RL. Now we found IB. So then if we plug in IB, we'll get beta times Vn times RL. Oopsies. This is out. So I guess they said VO. Oh, I said VO in two places. Uh, yeah, this can be V out. This can be VO. VO doesn't actually end up mattering for this question, which is kind of interesting, but not what we're focusing on here. Times beta plus 1 RE, and that would be V out. So now we have an expression for V out in terms of V in. If we want to rearrange this to get this kind of in terms of like a gain, so that would be V out over V in, right? This would become V out over V in equals beta RL over, oh, and I missed a plus sign there, sorry, over beta plus 1 RE plus RS. And then if you remember, either if you came to office hours or someone told you on the answer key, the expression that the textbook had at the back for this was that this is about RL over RE. And if you think about why, the idea is, okay, if beta is like really big, then as beta goes up, right? Just like how you learned like horizontal and vertical asymptotes in math class or whatever, right? This RS is going to stop mattering. And then beta plus 1 is just going to basically be beta. So the RS will go away. This will just become beta. And then you'll have beta RL over beta RE. And that's how you get that kind of answer. So basically the moral of the story here, right? This looks scary. You turn it into this, and then it's just something you know how to use. It's just, I did one loop equation, and that got me all the information I needed. Just always make sure you're keeping track of what information you actually need. In that case, this was IB. And then if we do this loop, we have IB, we have IB plus 1, or B time beta times IB. And you from this, you can get enough information that you can just solve the whole problem. So basically, if you don't know what to do, try writing a loop equation, try writing another one, and try to do it on parts of the circuit that you know everything about them already. And yeah, so that's how you do that one. Hopefully, upon seeing that, it's a bit more clear. And yeah. Um, yeah. As far as I know, I don't know what is on the quizzes, but if there is a transistor question, I imagine it won't be too complicated. It'll just kind of be understanding that the transistor is analogous to things you have already learned in class and then using that accordingly. Okay, moving on, I will talk about op amps. So op amps, I will start by talking about, could either start with the ideal or the non-ideal. Um, I'll start by talking about like what their purpose is. So it's an amplifier. It has a positive input and a negative input, which in this class you've probably learned as like VP and VN. And then in the most basic case, if you were to just put some voltages on here, the output would be some gain A times VP minus VN. Uh, because of how op amps are used, most op amps in the real world, like the ones you'll use in class, A is big. So like if your so what that means is if your VP is like a sig like 1 volt above your VN, then this will just go as high as it can go. So if this is positive, then this would go as high as it can go. If this was negative, it would go as low as it can go. However, since we use negative feedback, that's not what actually ends up happening. However, one thing that I will note is that the op amp, of course, has to get its output voltage from somewhere. So as you'll see in the labs, or as you've maybe already seen in the labs, I'm not so sure, it does have an actual positive and negative input. So one thing to keep in mind is when you're doing op amp questions, uh, if the thing you end up getting for the output voltage is above VCC or below VCC, it can't actually be there because it needs to have that voltage supplied somehow, right? So one thing to keep in mind is that V out will always be like between those two values. Yeah. Anyway, so that's the basic model. However, when we're actually using op amps for useful things, we don't want a gain of like a billion or a million, right? We want a gain of like 5 because that's more useful. So what we do is we use them in negative feedback configurations. And this makes it so that the behavior of the op amp is very predictable and straightforward. Uh, for the purposes of solving problems in this class, what that means is that if you're given an op amp question, the op amp will behave such that Vn will end up being driven to be exactly the same as Vp. So for example, the most basic op amp circuit is the inverting amplifier, which hopefully you have seen by now. And it is usually drawn like this, where you have some input voltage and some output voltage, and you have some two resistors, R1 and R2. And basically, the idea here is that our VP is fixed to 0 volts, right? And since our VP is fixed to 0 volts, when we give it any voltage, right, this output is going to like have a value because it's A times VP minus VN. However, this is not directly connected. So as this goes up, this will change the voltage back here. And this will kind of keep going until this value is driven to be like ever so slightly different from this value so that when you multiply this, it'll make everything work out nicely. This is kind of hard to put into words, but the conclusion is this. This is literally all you need to know, that Vn will be equal to Vp. That's really all you need to know for the ideal op amp model. One thing I will note is that there will be some current coming out of here, so we don't actually know what that current is. What that means is that you cannot do a node equation at V out. I'll show you what I mean in one of the example questions later. But basically, when you're doing questions with op amps, you can only do a node equation at like Vn or Vp because the idea is that there's no current going in here and there's no current going in here. So you know the current here, you know the current here, you know all the information needed for KCL. So whereas if you were trying to do this at the output, since there is some kind of current going in or out of the op amp, you can't do a KCL because you don't know what that current is. Anyway, the one takeaway though is that this system will behave such that it makes Vn be equal to Vp. And then whatever V out like causes Vn to be equal to Vp will be your output. So for this specific scenario, right? And I'll add that here. So there's no current going in for the ideal case. So for this specific scenario, for the inverting amplifier, let's solve to find out what V out would be. So in this case, okay, we know that VP, let me erase these arrows. We know that VP is 0 volts because it's directly connected to ground. And that means that Vn is 0 volts. So Vp equals Vn equals 0. If we want to find V out, okay, then we can do a node equation at Vn, right? Because Vn is connected to both Vin and V out. If we do an equation there, we'll be able to get an answer for how V out relates to Vin. So if we think about this like a KCL at Vn, just like how you did with node voltage, it's going to be, okay, Vn minus Vin over R1 plus Vn minus V out over R2 equals 0, right? Because remember, there's no current going into the op amp. However, we already know that that Vn is 0, so this is actually negative Vn over R1 plus negative V out over R2 equals 0. And then if we solve for stuff, so let me just do the math. We're going to get V out over R2 equals negative Vn over R1. If we then divide by Vin and multiply by R2, we'll get V out over Vin equals negative R2 over R1. And this is why it's called an inverting amplifier, because what it's telling you is that you have some gain. So if you put 3 volts here, and the ratio between R2 and R1 is like, let's say R2 was 9 kilo ohms and R1 was 3 kilo ohms, then that would get you a gain of negative 3, right? Because of this. So then you'd have negative 9 out there. So that's why it's useful, because you can just like tell it what gain to give you. But anyway, for most op amp circuits you're going to do in this class, the strategy is find Vn or Vp, whichever is kind of independent of the rest of the circuit. Okay, then Vn equals Vp, and then do a node equation at Vn or Vp, whichever one we haven't already looked at, and then solve for V out. And usually that'll be like the method. That should work in most scenarios. Okay. Then I said I would briefly touch on max power. Oh, wait, and then, okay. However, this is the ideal op amp. The non-ideal op amp, which of course all real op amps are, is that we model an op amp as such. So this is our positive and negative terminals. It's, of course, there's not actually zero current flowing in, because if there was zero current flowing in, then the circuit would have no idea like what the voltages are. So there's actually some big resistor. And then on the output, it's not actually just creating a voltage, of course. There is some kind of, I think I need to make this much bigger like they have it in the textbook. So we have some resistor there. And then on the output, we actually have some kind of dependent voltage source, which would be A Vp minus Vn, right? And then there is some kind of resistance going out. So this we could call R out. And usually this is going to be pretty small, maybe like 80 ohms or so. As you've worked in the lab, surely I think you should have realized like generally like stuff under like a kilo ohm, under 100 ohms is like pretty small. It'll burn really easily. So 80 ohms is like pretty small in the grand scheme of things. But this is the non-ideal op amp model. However, if A is really big and this is pretty small, then you'll find, oh, and this is like R in, and R in is big and R out is small, then you'll find that this circuit will end up behaving very, very similar to your ideal op amp model. Um, like as you do the math, it'll behave pretty much identically. And in the same way where I talked about for the transistor, we can literally just drag and drop in, okay, we know our base or our collector, base, and emitter, and we know that it corresponds with three points on our circuit model, and then we can drop it in. Or you can do the exact same thing with the op amp, where, okay, this is saying we have our model looks like this, and that would be exactly equal to here. So if I called this VO, VP, and VN, then if you were given a question where it told you to, okay, now use the non-ideal op amp, then you would just replace that with this circuit model and then solve it how you've learned to solve it in the class. You might have to rearrange some of the parts of the circuit to make it make more sense for you. As long as you're not changing connections, you can change how the circuit is drawn no matter what. So like instead of having, I don't know, I don't have a good example, but basically just as long as your wire connections stay the same, you can redraw it however you want and make it look like something you might have done more in class, and then that might help it make more sense to your brain. However, since this is kind of a very time consuming, I don't know how they would incorporate that into a quiz question, but it's still good to understand how they work on a fundamental level. Okay. And then really briefly, max power. This is just like something that's good to know. If you have some circuit and you turn it into a Thevenin equivalent circuit, and you want to find, okay, what resistor can I put here where this resistor will dissipate the most power? If you think about it, right? If you think about it, if I make the resistance too high, then the current goes down, which is going to be low power. If I make the resistance too low, then the voltage is going to go down, which is low power, because remember P equals IV. So what we want is there's got to be something in the middle where we get the most power. And what that turns out to be is just you'll dissipate the most power when RL equals RTH. That's the whole thing. And if you find RTH, the power dissipated through this load resistor will end up being what is it? It's like 4 V squared over R or something. Or V squared over 4 RL, I think. V squared over that feels right. Right? Max power. Let me see if I can find this in like 2 seconds because I forget the equation. However, if you know, like you don't really need to remember, this is one of those equations you don't need to remember because you can just solve it really quickly. Because like if you have, yeah, I'll just derive it real quick. Because if we know that this is the case, right, then the current is going to be V over 2 RL, right? Because they're the same. It's RL plus RL basically. And then if P equals IV, because of a voltage divider, the voltage over RL is going to be 1/2 of the like Thevenin voltage or the input voltage. So then we know P equals IV. We found I through the RL and we found the V. Then it's going to be V over 2 RL times 1/2 V. And then that would be V squared over 4 RL. Yeah. So that's just where those equations come from. It's a good thing to know. You might have to do that on a quiz. Yeah. If you want to figure out where this comes from, like you'd write the equation for this, and then if you take the derivative, you'll get a thing, set the derivative equal to 0, you'll find a maximum. And that's where this comes from. But basically, if you know this and you know this, you'll be set. Okay, I still got half an hour. I can just do practice problems now. Okay, so this is a pretty straightforward op-amp question, similar to one I did before, but um, slightly different. Oh, okay. So this is asking you to find V out, and I have not filled in any of the numbers yet. My bad. Oh, I missed oopsies. Okay, so here's our circuit, and it's asking us to find V out. So if we think back to that kind of order of operations I recommended, start by finding Vn or Vp, and then remembering that Vn equals Vp, and then do a node equation at that second one. So let's look at this circuit, right? Remember that there's no current flowing here, so we can ignore these. Which one of these is kind of independent of V out? It's going to be Vp here, right? So if we want to find Vp, then we can start by just doing a node equation at VP, or you can do kind of however you want to find VP. In this case, it's going to be easiest if we do node equation at VP, or you can call it KCL, same thing. Here, we're going to have VP minus 0.5 over 80K plus VP minus 1.2 over 64K equals 0, right? And if we multiply both sides by, it's annoying. Yeah, I guess. Okay. I'm just gonna skip to the answer. You can do the algebra. It's not gonna look nice on my paper. Oh, don't do it. Okay. If you multiply both sides by 10,000, yeah, sure. VP minus 0.5 over 8 plus VP minus 1.2 over 6.4 equals 0. Then we have VP times 1/8 plus 1 over 6.4. This is just how I'm going to do it because it is pretty straightforward to do on a calculator, even if it's looks kind of odd on the paper. Hopefully you can see how I did that. If you just like split these, right, you'll have VP over 8 and VP over 6.4. So that's how you get this half. And then this part and this part get moved to the other side. And then this you can very straightforward, just like in your calculator, you can say, okay, I have this divided by that, right? And then that'll get you VP quite easily. So this will end up getting you VP equals 0.89 volts. And then that's telling you, okay, also Vn equals 0.89 volts. Now, third step, we do, okay, node at Vn. And we're going to then say Vn minus 0 over 18K plus Vn minus V out over 72K equals 0. And in times like this where you end up having like weird numbers, it can even be better to just leave Vn as a variable until the end and then plug in the 0.89. Doesn't really matter which one you pick. You'll get the same answer, of course, but can make your math just kind of feel easier. In this case, if we multiply, I think 72, is that a multiple of 18? That'd be crazy. It is, it's a times 4. Okay, so if we multiply both sides by 72,000 or 72K, we'll get 4Vn plus Vn minus Vo equals 0. So that tells us that Vo equals 4Vn, or 5Vn, sorry. Yeah. And if we plug in Vn, we'll get that V out equals 5 times 0.89. That's not equals. And then that would be V out equals 4.45. And that would be our answer here. So again, it's a pretty straightforward process, right? You find the voltage at one node. In this case, since this is just voltage sources, has nothing to do with the output, it's pretty straightforward to just, okay, look at this, we can find VP. You know how to do that. Then, once we have VP, we also have VN, because the way op amps work, it'll end up making VP equal VN. And then once we have VN, we can do a node at VN and use that to find V out. And that's all we did. So pretty simple math. Just don't get tripped up by like algebra. It's pretty straightforward though. And now I will do more op-amp questions because that is it's something that's good to know. Okay, this one looks a lot more complicated, but really is still done exactly the same way. Um, this is a two-stage op-amp question, in which case where we have two op-amps. Crazy. However, it's still like the exact same process. I'm I like using this arrow a bit more. I think you've been using the this in class, but technically, if you're being really particular about it, this is like earth ground, and this is just analog ground or just 0 volts. And this is also slightly easier to write, so I'm going to use that. This is going to take me a minute because it's kind of big. Okay, so this same thing, find V out. This looks pretty complicated. However, we can still approach it the same way we did before. We're going to want to do it kind of one op amp at a time. But once we're doing that, it's still the same process. So again, it's going to be find VP or VN and then do a node equation at the other one and then repeat. So here, we can start by looking at this part off to the left. So we can ignore everything to the right, not looking at that right now. We just want to find this V out one. I'll call this VO1, and then this can be VO real. So we're trying to find V out one. And first, okay, which one of VP or VN can we find very easily? Here, it's going to be VP. Don't get tripped up when you have a resistor here, because remember, there's no current flowing in here. And if there's no current, then the voltage drop over a resistor, which is V equals IR, is just 0 because there's no current, right? So that means if we have 1 volt here, then we also have 1 volt here. Because this resistor, there's no current flowing through it, there's no voltage drop. So what that tells us is that VP equals 1 volt, same as VN. And I'll call this VP1 and VN1 because there's two of them this time. Now we have VN1. And just like we did in the last question, exactly the same, right? We're going to do a node at VN1. So at VN1, we got VN1 minus 2 over 4K plus VN1 minus V out 1 over 24K equals 0. I'll do the same thing I did last time here, where I kind of separate the variables and then leave them kind of in fraction form. So we'll get, what is this? Actually, I'll just fill it in. This is too many choices. We'll get if you multiply everything by 24, actually, yeah, just multiply everything by 24 here because those are nice numbers. You'll get 6 VN1 minus 12 plus VN1 minus VO1 equals 0. Then if you shuffle things around, V out 1 equals 12 minus 7 VN1. And VN1, of course, is just 1 volt. So it's 12 minus 7. And that'll get you 5 volts. Or wait, I might have messed up something. I think I messed up something. Should be negative 5 volts. Hold on. Because you add that over. Oh, yeah, yeah, yeah. I did two negatives here when I should have only done one. Yeah, 7 VN1 minus 12. And then this is 7 minus 12. And then that gets you negative 5 volts, which is fine because if we remember, usually you give them a positive and a negative supply. Very cool. So we found that V out 1 is 5 volt or negative 5 volts. And now we have to move on to the next part of the circuit. Again, we want to find, okay, is VN2 or VP2 easier to find? This is VP2, VN2. And if we look, while we do have V out 1, and that's related to VN2, this is no different than having this voltage. And since we still don't have V out, we still don't know how that will affect VN2, even if we know how that will affect it. So we're going to find VP2, because this is very straightforward. You can either do it in the same way we found this node here, where we did a node equation, or if we look at it, we actually really have, in effect, just a complete circuit here, and this can be thought of as a voltage divider, so that's what I'm going to do. So at VP2, we have VP2, I guess isn't really an at, but we can just say, because of voltage divider, VP2 is going to be equal to 3 volts times 4K over 2K plus 4K. And this is going to be two sixths of, or yeah, 2/6 of 3, which is just 2. Crazy. So we found that, and then that's also VN2. Now we can say, okay, at VN2, we're going to do the exact same thing. Wow. VN2 minus V out 1 over 20K. I'm going to write it all in variables here first, just to be very clear. If we multiply by 40K, we get 2VN2 minus 2V out 1 plus VN2 minus V out equals 0. You're going to get V out equals 3VN2 minus 2V out 1, which if we plug things in, we know VN2 is, make sure I'm 3 times 2 minus 2. Um, yeah. I'm doing it right, I think. Yeah. Yeah, we'll get V out equals 3 times 2 minus 2 times negative 5. So this will end up being plus, right? So it's 6 plus 10, and V out equals 16 volts. Wow. So again, you look at how much math I did, it's really not that much math. It's one equation, two equations, three equations. And it's still a pretty straightforward process. Find one of them, do a node equation, find the next thing. Find one of them, do a node equation, find the next thing. And yeah, this would be your final answer. Cool. And I still have another 15 minutes, so I will do more op amp questions, I guess. Find a good one. Let's see. Um,
I have a question. If you don't have like any specific question that you want to go through in, can you please go through like the first part of problem 4 of the
um,
homework?
yeah, I could do that.
Thank you.
Let's see. That was the one with the kind of we.
That weird shape of
Yeah.
resistors together. Yeah.
Okay. So that question was saying we had yeah, that was bad. Okay, we had this R1, R2, R3, and R4 minus plus we had VS, and then that was going to Forget how exactly it was drawn on the homework question, but I'll draw it like this. That and RF minus plus. Yeah. So the two parts of this were if this is a forget exactly how was forget exactly how it was phrased, but it was basically find the Thevenin
Yeah,
equivalent.
that's A, and then the bottom part is B.
Okay. So if you think of it like this, and then this is B, right? Yeah. So it was find the Thevenin equivalent of this part of the circuit, right? And then use that to find V out. Yeah. Yeah. Explain if yeah. Okay. So to start, for the Thevenin equivalent, we're going to completely ignore everything to the right, right? Because we're just trying to find the Thevenin equivalent of this circuit. So we have, I'll copy it. The first thing I would do to make it make a bit more sense is redraw it in a way where it is a bit more clear what is going on, I guess. So I don't really like seeing all of those not right angles. So I would write this like we have this, 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 and this is our B, and this is our A, right? So, yeah, let me make sure I know what I'm talking about before I start talking. Okay. Yeah. So if we want to find our Thevenin equivalent, of course, we need our VAB, which is going to be our VTH, and we need an RTH. We can start by finding our VAB. If this is R1, R2, R3, and R4, okay, if we want to find VAB, remember that's also VA minus VB. So if we can find VA and find VB, then we're good. So the way we do that, well, actually, first off, we know, hmm, what's the explicit way they say to do this? Um, uh, that's, yeah. Okay, yeah, they just say do mesh current, which makes sense because it's you have two loops. You can do mesh current. You could do that. So let's say, I think my Apple Pencil's dying. It's making a lot of gaps. So we have I1 and we have I2. Ignore this. This is not important. Because remember, B is already defined as 0 volts. So it's really just VA. Okay. Anyway, for I1, we're going to have a loop. If we start with that voltage source, it's going to be positive Vs for I1 plus R1 I1 plus R2 I1 equals 0. And we'll end up finding that I1 equals negative Vs over R1. Oh my God, my Apple Pencil, please. R1 plus R2. And then for I2, we're going to have negative Vs because it's going the other way now, right? And then R3 I2 plus R4 I2. And we find that I2 equals positive Vs over R3 plus R4. And then with that, we know that, what's this? Does that make sense? Oh, yeah, that makes sense. Okay. Yeah, and then since we know the current going through, we can kind of pick either way we want to go. Since we know we have 0 volts here, and we know the current going through this resistor, and we know the current going through this resistor, we can basically say, okay, we know this, and we know this. So it's just going to be 0, go up this voltage, go up this voltage, and then we'll have VA. So what that's going to look like is going to be, okay, VA equals 0 volts, which we can think of as like our starting point, plus R3 times I2 plus uh yeah, R1 times I1. That's maybe a bit unclear, but hopefully the illustration I just did were like, okay, we found this current and we found this current.
I
Then
have a
we
question.
Mhm.
The voltage source in the middle, is it not causing any problem for you to just move from R3 to R1?
Um it has not particularly since they're connected basically since we found the current here and here that this
Mhm.
current will already like factor in the effect of that voltage source because if we look it's in the equations for both, right? So
Okay.
since for a resistor this is like always true, right? If we know its resistance and we found this current, then nothing that this voltage source does will change the fact that we can get V equals IR to find that voltage. Of course, the I is not actually known. It's like a function of the voltage, so it's still affecting it. But that's that's what we can do there. That's why this works. Basically, this is VR3 and this is VR1, and that's what we're doing. So if we do this, we're going to have R3 over R3 plus R4 times VS. I'm just kind of rearranging it a little bit. And then it's going to be minus R1 over R1 plus R2 VS VAB, right? And then if we factor out VS here, we'll get VS times R3 over R3 plus R4 minus R1 over R1 plus R2. And that would be our Thevenin equivalent voltage. Luckily for us, the Thevenin resistance is much easier. Um, yeah, yeah, it is. Okay. So if we get rid of that voltage source and we keep the same equation we had before, so our voltage source is, or we keep the same diagram we had before, right? This is pretty clearly going to be, okay, these two are in parallel, these two are in parallel, and then we're going to add them together. So I'm going to even write that in one equation. So just RTH is going to be, the symbol they use is for parallel is like 2 bars, like because they're parallel. So R1 in parallel with R2 plus R3 in parallel with R4. And then if you want to write that out, it would be like R1, R2 over R1 plus R2 plus R3, R4 over R3 plus R4. And that would get you your RTH. So then these would both go to, albeit a kind of bulky variable form, but if you were to have values for these, you could just plug it in and get actual numbers, where we have R1, R2, R1 plus R2 plus R3, R4 over R3 plus R4 as our resistance. So this whole thing is our resistor. And then our voltage source would be Vs times R3 over R3 plus R4. That's a 4, 4. Oopsies, R4 minus R1 over R1 plus R2. And then that whole thing is your voltage. Anyway, so now that we have this, I'll go on to the next part of the question.
How is uh how is it that wait, how is it that R3 and R4 not in series as well as R2 and R1 in series?
Because if you take, right, we saw from here, this is what it looked like, right? If we take,
Yes, yes.
yeah, we take that, turn into that.
Yeah.
So we're here. If we want to go from A to B, right? We can
Okay.
think of this, if we redraw the circuit, it might be make a bit more sense if I draw it like this. But if you notice, all the connections here are staying the same, right? I'm just kind of
Mhm.
changing what the wires look like. If we draw it like this, to get from A to B,
Okay. Okay.
yeah, yeah, you
I
can
get
go.
it.
Okay, cool. Yeah. So basically just think of it like that. If you have something confusing like this, it's often helpful to change it to something like that. Yeah, it can go through either of these, so those are in parallel, and then it can go through either of these, those are in parallel. And then you have this section, you add them together, and that's how it got that. Okay. So then if we want to then find Ooh, wow, that lines up so well. We're trying to find V out over VS. Then from here, we just kind of do the same thing that we did in these equations I showed before. First off, because this is connected here, we know that VP equals 0, so VN equals 0. If we do a node at VN, we're going to get, I'm going to call this RTH and this VTH because I'm not putting these all in those equations because that'll take too long. So we have Vn minus Vth over RTH plus Vn minus V out over Rf equals 0. If we then solve for V out, we're going to get, if we think back, this is actually identical to this inverting amplifier case I did earlier, where we're going to end up getting negative R2 over R1. So I'm going to skip that math. Same as inverting amplifier, where we're going to end up getting that V out equals VTH times, yeah, RF over, or negative VTH over RF times RTH. So if we're trying to find this, we just divide that over. Or actually, we're not quite there. We have to plug everything in now, which is where it starts looking ugly. So it's negative VS times R3 over R3 plus R4 minus R1 over R1 plus R2 times RF, which is just a single variable, right? Over RTH, which is that whole expression R1, R2 over R1 plus R2 plus R3, R4 over R3 plus R4. And then if we want to find V out over VS, we take our equation again. I'm not writing all that again. We're here. And very simply just move the VS to the other side. And that would be your final answer. And if you want to like plug stuff in, go for it, but you could really just leave it like that and no one would complain. This probably like I imagine these two terms will cancel each other out in ways, but I don't really want to think about that. But yeah, basically it's still the same as stuff you've done before. It's just you have to plug in the variables that you found from the last part of the question. Yeah. Okay. Time is about up, so does anyone have any last minute questions? Okay, in that case, I will end it here. Good luck on the quiz tomorrow. Hopefully this helped. And yeah, bye-bye.